1 p.m. Gyan has indicated that he can stay on for a few minutes thereafter to engage in any discussion, dialogue that people may have. The slides will be available at the end of the presentation. Log into your Milibo account to view them. And while we are recording this session, Gyan and I have to discuss potentially some copyright issues, based on the people who have funded this research. So once those issues get resolved, we will, put the recording up, or else you might have to content yourself with the slides, or basically talk to Gyan for more details. Please keep your telephone or microphone muted at all times. Only unmute yourself to ask questions. If you've dialed into the conference by phone, you must have entered your audio pin. I can only unmute you if you do so. For those of you who prefer to ask questions via instant message, there's a chat window. Please ask your question there. Gyan has indicated that he welcomes questions and dialogue, so please ask questions, share your comments as you have them. So with that, let's go ahead and get started. Today we are delighted to have Dr. Gyan Ranjan to talk with us about incremental computation of pseudo-inverse of Laplacian theory and applications. Gyan is a senior member of technical staff at NARIS, which is a wholly owned subsidiary of the Boeing company. He received his PhD in computer science from the University of Minnesota, Twin Cities, Minnesota, in the spring of 2013. While his day-to-day work involves machine learning algorithms and their application to cybersecurity, analytics, and systems, his research interests also span algebraic graph theory, complex network theory, and at times intriguing yet pestering Diophantine equations, some of which he wishes to find solutions to in the not-too-distant future. So, though the title looks scary, Gyan tells me that the Laplacian is a super important thing in present-day applications and networks, etc. So with that, I'm going to go ahead and turn it over to Gyan. Gyan, can you please go ahead?
Yes, thank you. Good afternoon, everybody. This is Gyan Ranjan, and I'm going to be talking about an incremental computation approach to compute pseudo-inverses of Laplacians. I will also discuss, I will keep the applications part more than the theory part, just to accommodate a broader audience. And even though it sounds, at least prima facie, it might look that it is very dense, it's not going to be that. So I'll spend a considerable amount of time during this presentation focusing simply on application scenarios. And then we'll delve a little bit deeper into why we need different kinds of methodologies to compute this very important matrix pertaining to graphs. So as the title suggests, this research was primarily conducted during my PhD at UMN and formed a considerable part of my thesis, which had an overarching goal of understanding interdependencies and vulnerabilities in complex networks, both static and dynamic. So Sridhar, I think, has already covered this housekeeping etiquette kind of stuff, so I'll not go into it in detail. Let's move on. So the presentation will comprise of 4 sections. First, I'll present the motivation for this kind of study, again with a broader audience in mind. I will then introduce notation that we need for the treatment of this subject that can be slightly more daunting for a first-time viewer, but it's nothing out of place. All these terminology people use irrespective of whether they have worked in the field of data mining or anything to do with binary networks, where there are two-party communications. We'll then go into the incremental computation of the Laplacian. We'll discuss a divide and conquer approach, and we'll show how the same approach can be adapted to growing time-evolving networks so that you don't have to compute the pseudo-inverse from scratch, which is a very expensive computational step. In the end, we'll show, if time permits, that this insight that we gain in computing the pseudo-inverse in a divide and conquer with a divide and conquer approach incrementally also shows us that if you had interdependent networks, what role does combining nodes of different kinds play if you have 2 different kinds of networks that you want to merge together? A very clear-cut case is that of power grid networks, which are increasingly controlled by a communication overlay network on top. And as I'll discuss and show a scenario, there was a failure in 2003 in Italy, and by the failure of only a couple of communication nodes in the communication part of the network, the entire Italian power grid came crashing down. and could not be recovered for over a period of 2-3 days. So there are lots of interesting applications of this sort of study, even though the treatment of it is largely mathematical. So let's start with motivation. Our principal thesis in understanding or discussing this sort of a subject is that all the world is a network. Actually, complex networks as a field are sort of a new wine in an old bottle, or rather old wine in new bottle. Graph theory has had its existence and applications in areas of topology, as well as in areas of applications to computer science for a long time. Complex network theory is simply a reincarnation of this. And basically all that complex networks are a collection of entities and the interconnections between them. This can vary depending upon the field of study in which this sort of terminology or formulation is used. For example, you can see the applications of complex network theory in structural analysis, where one of the principal questions that people study is the structural integrity of certain kinds of networks. This could be your router infrastructure that is used to deliver end-to-end communication between internet hosts. It could be power grid networks in which there are certain power production centers connected through long and yet vulnerable power transmission lines. This can be social networks such as Facebook or Facebook, Twitter, etc., in which different people have different kinds of communication links and different kinds of relation links going between them. They can also be extended to biological networks. Most famously, the study of S. cerevisiae, which is the yeast, common yeast, whose proteome has yielded a lot of good inference for the biological community and so on. In order to study a complex network, one of the most commonly used tool is actually a graph representation of the network. So the network is principally abstracted in terms of the participating entities, which are called nodes, and the interconnections between them, which can be modeled as edges or links. So a graph-like modeling is a natural consequence of this formalization. In order to study graphs...
Yeah.
Yes.
There's a question here.
Sure.
What makes a network complex?
So basically, in terms of terminology, a complex network simply means that the cause or effect of structural behavior of one node is not limited merely to its neighborhood. A complex network can have multiple layers. So as I was giving an example, one of the examples of a complex network would be a smart grid power distribution system, in which you have a communications network that is overlaid on top of the power production and distribution topology. The communication network then controls the distribution of power through this power grid, and the power grid network supplies the electrical motive power that is required to run the communication network. So there is an interdependent component to this. Networks are complex if they have multiple different kinds of interactions that can go on between either individual nodes in them or between different sub-motifs present within those networks.
Okay, thank you. By the way, for folks that are asking questions via chat, once I relay the question, if you need to follow up, either send me a follow-on or else unmute yourself and follow on directly. Thanks, Gyan.
Sure. So one of the most widely used tools in the study of graphs and consequently of networks is the Laplacian of a graph. And more specifically, the combinatorial Laplacian of a graph. But the Laplacian itself, although while in some cases the Laplacian itself provides certain structural properties of the graph, for many different and more complicated properties that we are interested in, we also need to compute its pseudo-inverse. To give you a few examples, structural centrality of nodes and edges, which tells us how significant a particular node or an entity is in the network for the overall connectedness of the network, or how important is a particular link in the network with respect to the overall connectedness of the network. These characterizations of node significance and edge significance can be directly mapped to the entries of the pseudo-inverse of the Laplacian. A more commonly used application is the graph partitioning algorithms. Laplacians find massive usage in all kinds of graph partitioning algorithms, and as our computer science fellows would agree, partitioning is one of the more important and challenging problems in the study of combinatorial structures. Yes.
One more question.
Sure.
What is in a complex network? What insight does the Laplacian capture?
So we'll get into the details of that immediately after this slide. So if you can hold that question for a minute.
Thank you.
Okay. So similarly, we also have an entire field has spawned, which is called graph mining and motif identification in different kinds of evolving networks, time evolving networks, etc. The key insight of all these applications and all these methodologies is that real-world networks are sparse, which means that not all nodes are directly connected to other nodes. They rely on some intermediary nodes and the interconnections going between them in order to communicate with farther nodes. Also, the primary thesis of this sort of work is that structure of a network actually determines its functionality. So how robust a network is entirely dependent on how its structural components gel together. So, putting the cart before the horse, as I was talking earlier, here you see on your screen two different kinds of networks that originate in entirely different scenarios. On the left-hand side, what you have is a skeletal representation of the Western States power grid network that supplies motive power to states California, Nevada, and so on and so forth in the western half of the United States. As you can see, that certain power production plants that lie at the core of the network or even at the periphery require a very complex maze of interconnections that help distribute the power load. It is vital to understand if there are certain kinds of bottlenecks within this network that, if targeted by an adversary, can bring down the entire network altogether. And as time has gone on, I think these networks have become even more complex because there are now plans of combining all of the different parts of the smart grids in the US. On the right hand side, you see a network sciences co-authorship network that is, every node that you see in there is actually a researcher, and there is a direct link between two researchers if the two researchers co-authored a paper. And this was taken from the community of physicists, mostly statistical and mechanicalistic physics. Now, what you can see that despite side, that would mean a disruption of ideas, whereby no two people can collaborate if they lie in two different halves of a subcommunity and so on. The coloring that you see on these in these two graphs of the nodes has been derived entirely from the elements of the Moore-Penrose pseudo-inverse of the Laplacian, the matrix that we are so eager to compute and about which we will talk in the rest of this. Immediately you can see that if I told you that the size of the node is actually its significance as determined by the Laplacian, it is pictorially evident that the more centrally placed nodes get a better value in terms of what we see in the Laplacian. Hence, there is a direct correlation between the value attained for these nodes in the Laplacian pseudo-inverse distribution and their actual structural location in the network. Red being the better, more important in terms of overall connectivity, and going all the way through yellow, orange, turquoise, and so on and so forth. Towards the periphery, the color fades out. But it's not only limited to nodes analysis. We can also extend this to saying if there was a connectivity link between node A and node B, how important is that link for the overall connectivity of the network? And once again, you would see that the coloration of the edges, although it's not very clear, and for very good reasons. Graph plotting algorithms, graph plotting tools are still very rudimentary and can't accommodate a lot of things. But you can see that it's still, from the center to the periphery, you see that the distribution goes away and follows a direct correlation with the structural importance. A better way to visualize this, I'm now plotting these two things in a matrix form. So the nodes have been arranged on the x and y axis in terms of their significance in the network. So the closer it is to the origin, the more structurally important the node is. And the color of the dots shows that there was an edge between these guys. And the significance then goes from blue to red, which means that more blue it is, the more significant the edge is, as opposed to more red it is, the less significant it is. Again, these values are entirely the values corresponding to those edge entries in the Moore-Penrose pseudo-inverse of the Laplacian. So in short, this one matrix gives us a lot of information about the network topology. We will now define precisely what this matrix is, what are its properties, and how the entries relate to the things that I have been showing you pictorially for now. So, but before we go there, a valid question would be, so who really cares whether we can compute this or not? Apparently a lot of people do. So this entire research was funded by an agency called the Defense Threat Reduction Agency, whose the thing that keeps them awake most of the time is, if there was a targeted attack over a geography, how much of the critical infrastructure in the United States come crashing down? Can we determine that a priori and therefore make provisions to make sure that the risk is mitigated? Robustness of infrastructure networks is one of the most important aspects for national security, and this is at this point in time very important to almost all countries in the world. Secondly, topology designers. So one has to understand that a network is a resource-intensive design, meaning that you have only so many nodes and so many interconnections that you can budget for. The question then that one can ask is, given a certain number of nodes for which you have budgets and the certain links that you can put in, what is the best configuration to put these links in so as to get a more robust, overall robust network? And by robustness we mean difficult to break up into multiple parts. This is also important, while this is even more critical while designing interdependent networks, in which two different networks have been designed at two different points in time. But the question that you want to ask is, where should I lay the interdependent links or interconnectivity links between these two networks so that the overall structure is very robust? Social media and advertisers also require this sort of inference, for example, to find out who are the influential nodes and links, how are communities shaped between these nodes, etc., etc. And last but not the least, poor graduate students who tend to deal with these problems and increasingly have to look up to very huge network data sets, such as the one on Stanford University's SNAP website. And you can't compute these matrices in the naive MATLAB-oriented manner in which you just blast everything into one matrix and try to expect results of the pseudo-inverse. So, notation. With that, let us define a few things before we delve into the technical details of how we compute it. So, network, in this formalization of a network will always be treated as a graph. A graph is basically a combinatorial structure which has vertices as entities and edges as interconnections. So if you think of Facebook, this could be, every profile page could be a vertex, and every friend relation can be an edge. So it's simply these kinds, a simple graph is, or a simple network can be abstracted as a collection of vertices representing entities and the binary interconnections between them that can be represented as edges. Note that that does not necessarily mean that the communication is always in the immediate neighborhood. For example, if I have a friend who has a friend, and I'm not I'm not directly a friend with the other person, I can still pass information through this intermediary friend, and therefore networks have multi-hop communication inbuilt into them. That is why graphs are a good way to study them. Now, we will consider all our graphs to be simple, connected, and unweighted for simplicity, but all the results that will be presented are extendable to weighted graphs as well, in which edges can have affinity weights, such as you are only, on a scale of 1 to 10, I consider you to be a friend at a scale of 9 as opposed to a scale of 7 and so on. The methodology is robust in that sense. Every graph has certain topological dimensions. The number of entities in the graph is called the order of the graph, and we will denote that by n, small n. Number of edges in the network will be denoted as a small m. And we define a quantity called the volume of the graph, which is basically the sum of all the individual degrees of nodes. A degree of a node is simply the count of how many other nodes the node is directly connected with. So, and if the graph is unweighted, it can be seen that this value is exactly twice the number of edges in the graph. Having said that, a graph as a topological entity is interesting, but we have to have a representation in which we can manipulate or understand what it has. So one of the representations that we'll be dealing with is the algebraic representation of a graph. A graph GVE can be represented in terms of its adjacency matrix, which is simply an n cross n matrix if there are n nodes in the graph. And we put a value of 1 if there was an edge between the two nodes I and j. So aij will have a value of 1 if there is an edge in the graph between I and j, and will have a value of 0 if there is none. There is a degree matrix, which is a diagonal matrix, which has the degree of each node on the diagonals and 0 elsewhere. The Laplacian, or the combinatorial Laplacian of the graph, is then defined as L is equals to d minus a. For a simple representation, I have shown on this slide the Laplacian of the graph shown on the top. It follows very simply, and I'm pretty sure that most of our audience will be aware of this particular matrix. Structurally, L is what we call a symmetric positive semi-definite matrix if your graph was an undirected graph. The term simply means that the eigenvalues of this matrix are either 0 or positive. They cannot be negative. But we will always assume that our graph was connected. If that's not the case, then we treat all independent connected components separately. But if the graph was connected, then this matrix has a unique eigenvalue of 0, which is the smallest eigenvalue. All the other eigenvalues of this matrix are positive, except the 1. This matrix is also doubly centered, which means that if you summed up the L entries of the matrix, either column-wise or row-wise, you will always get a 0. Something which looks very insignificant, but has a profound impact on how the geometry comes out. So let's move on to the geometry of the network. Remember that when we started with the definition of graph was simply a topological object. But wouldn't it be nice to then embed it into a space? All the people who work in the field of data mining and graph mining, etc., are familiar with the notion of a distance function. All spaces that help us evaluate some sort of similarity between entities in a data set require the notion of some kind of distance. And one of the best kinds of distances that we can work with are Euclidean distances. So in fact, the Moore-Penrose pseudo-inverse of the Laplacian, which is, as I said, the Laplacian itself is a positive semi-definite matrix with one eigenvalue 0, which means that its inverse does not exist. But a pseudo-inverse, or many varieties of generalized inverses of this matrix exist. One of them is called the Moore-Penrose pseudo-inverse of the L, with which we are concerned in this talk. This matrix L plus can be written in terms of the inverted eigendecomposition of the matrix L, so that if the eigendecomposition of the matrix L was U lambda U prime, all you have to do is you take the lambda matrix, which is the eigenvalue matrix, and except the eigenvalue 0, you take reciprocals of every eigenvalue, recombine them, and you get L plus. L plus, we can also see that this L plus can then be written down as a multiplication of an orthogonal matrix projection, which is x prime cross x. So without going too much into the details of this, what this means is that with the x matrix that you see after the decomposition in the second line, you get a Euclidean space which represents all these values. In that Euclidean space, the length of the position vector for every node has a coordinate. It's simply like being on a map, but this is an n-dimensional coordinate space. And the diagonal element of this matrix, L plus, tells you how close or how far away from the origin of that space a particular node is. More importantly, closer a node is to the origin in that space, which is determined directly by the element L plus II, which is the diagonal element for that entity. The closer it is to the origin, the more central it is, which means in terms of robustness characteristics, that is the node you want to attack if you want to bring down the network fast. Similarly, if you want to find out which edges to attack first in order to bring down the network fast, you look at the L plus ij entry corresponding to that edge, which is basically a cosine value. It's a multiplication. Again, for data mining folks, we know that pairwise interactions are better represented in terms of angular measures, and this L plus ij is basically an angular cosine measure. And finally, there is a distance function defined in the space which tells you the distance between two nodes I and j in this space is directly computable in terms of the elements of the matrix L plus ii plus L plus jj minus L plus ij minus L plus ji. This is a Euclidean distance. In fact, again, from machine learning and data mining point of view, the L plus matrix is actually a kernel function of the graph. It's a Gram matrix, and its elements represent inner products or position vectors for every element in the network. So far, so good. So the color distributions that I was showing you earlier in those networks were computed simply on the basis of these entries of the L plus matrix. So we define a measure called topological centrality, which is nothing but 1 divided by the diagonal element corresponding to that node in the matrix. So C star I is 1 upon L plus II. The reason is that higher the value of L plus II, more peripheral the node is. And converse is true, which means that lower the value, the more central the node is. Therefore, the 1 upon L plus II. Similarly, for an edge, you just look at the L plus ij value, and you can say whether the edge is peripheral or central. I would refer you, all interested readers, to a publication in Physica A that we had, which will show why this is not simply algebraic jiggery-pokery. It has very interesting topological interpretations in terms of subgraphs and participation in subgraphs. Due to limitation of time, I will not go into too much detail there. But you could also be interested in a problem which says, all right, given two networks with the same number of nodes and edges, which one of the two is more robust? Because then I could choose that as a better design as opposed to the other. It turns out that the trace of L plus, which is simply the sum of all the diagonal entries of L plus, gives you the Kirchhoff index. This lower the value of the Kirchhoff index, more robust your network is. This metric has been used in mathematical chemistry, biology, etc., to understand structural robustness and coherencies of molecular structures. And for those of you who are familiar with spectral graph theory, all of these entities actually align themselves very well with spectral parallels. I will leave the details to the interested reader for the elaborate papers. But so we have motivated that if you had a graph kind of a problem, or a problem that you can abstract as a graph, the Laplacian and its pseudo-inverse give us very good understanding. And by the way, I have only discussed a few applications. There are several more, and familiar readers would already know about it. But there is a huge literature about the application of these tools to different problems of graph analysis. The bottleneck that we suffer with these kinds of measures, as opposed to locally computable measures like PageRank, are the computational overhead. So that is going to be the crux of our discussion today. The Moore-Penrose pseudo-inverse is yes.
So I think this might follow up the previous question on sort of the intuitions behind the Laplacian. So let me ask this question perhaps differently. Would a network designer or a social network designer or the DTRA folks trying to sort of do a threat analysis for, let's say, the energy grid, for example, would they first take the existing topology, compute these matrices and these, the centrality, what do you call, indices, as you've indicated, and then figure out how to change the network, or is the design of the network sort of a precondition, or sort of an input into this process?
Both things can be done. So you can approach the problem in two different ways. If there is a network that has existed for a period of time, and you wanted to find out if certain tweaks made to the network would change adversely or beneficially the network, or where the bottlenecks lie and where you should reinforce your connectivity by putting in additional lines or making more disjoint paths, then this Moore-Penrose pseudo-inverse tells you where those bottlenecks are. But if you had to design a new network from scratch, then all you need to feed in is the number of nodes that you have, the number of entities that you have in the network. These could be routers or power production units or whatever, and some basic count on the provisioning resource. For example, you could say, I will only spend 5 million metric kilometer lines of transmission wire. Now you can form this as an optimization problem, and trace reduction problems have been studied in the field of semi-definite programming and optimization very well. So in the end, what you would expect is that graph which minimizes the trace of the pseudo-inverse of the Laplacian. And that would be the output to that sort of a question. So whether you want to design a network a priori, in which case this becomes an optimization problem, and or whether you want to study the properties of a pre-existing network, in which case these metrics have to be computed in order to understand where the bottlenecks lie.
Thank you. So then the intuition behind the Laplacian is simply that using this, the Laplacian, I'm able to figure out in a very, very large network what are sort of the important nodes, important edges that either I need to reinforce or protect. Is that correct?
Yes.
Thank you.
But more from the point of view of communication and infrastructure networks. All right. Okay. So one of the bottlenecks that people face, and this pertains to almost all areas in which. So initially, when this theory was developed or these tools were being developed, people only dealt with small networks, and hence computation of pseudo-inverse was, although it was a bottleneck of sorts, it was never a daunting task. Traditionally, pseudo-inverses are computed in mathematical tools like MATLAB using the standard SVD method. An alternative method is also known for computing the pseudo-inverse, in which you do a minor perturbation by adding a constant factor to the Laplacian, and then that makes the Laplacian invertible. Neither of these methods are computationally feasible for the kind of networks that we deal with today. You have millions and millions of nodes in networks these days, and both these methods have a computational complexity of the order of n cube. Even parallelizability of the inverse computation methods is very difficult and incurs a lot of I/O overhead. So one of the challenges that has been, or rather one of the things that have been a handicap for the adoption of these methods or implementation over large-scale networks is the computational overhead. But to give you an example, or just a feel of this, here is an experimental study conducted over varying degrees and varying connectivity constants for Erdős-Renyi graphs. With two different P parameters, which is basically the density of edges in the network. What you can see is that in both cases, the normal pseudo-inverse, P-inv, and the perturbed inverse computation grow almost, shall we say, well, if not, they grow drastically with the number of nodes in the network. Actually, we know that this is both these things in their sort of how should I say, asymptotic case, both the algorithms have an order n cube complexity, even though the PERT actually takes slightly less time in practice. We can see that the curve is simply abound towards an increment. The second problem with these two approaches is that they are agnostic to the sparsity of edges in the network. So even though you may have a very sparse network, the amount of computation required to compute the pseudo-inverse is almost agnostic to that in the traditional sense for a very simple reason. Even though a graph is sparse, its adjacency matrix and its Laplacian matrix are both sparse, but the pseudo-inverse is always full. So let me repeat that. Irrespective of the sparsity order of your graph or network, all the n squared elements of the pseudo-inverse have a non-zero value if your graph was connected. And therein lies the challenge. Hence, we know that there is a lower bound on the computational cost of pseudo-inverse. It can never be below order n squared, which in itself is daunting, but then can be. But obviously, parallelizability could be a way of offsetting that cost or challenge. So, as I defined previously in a slide where I was talking about the geometry of the network, remember that there was a distance function defined in terms of the elements of the pseudo-inverse of the Laplacian. Given any two nodes x and y, we define something called an effective resistance distance between x and y, which is represented in terms of the elements of the pseudo-inverse as following. Omega xy, which is the effective resistance distance, is equal to L plus xx, which is the diagonal element for the x entity, L plus yy minus L plus xy minus L plus yx. So in the geometry of the network that is captured by the eigenspace of this matrix, the Euclidean distance is actually a physical quantity. This physical quantity, just to give a bit of context, is the same if you considered your network to be an electrical network. So, given any kind of network, if you wanted to form its electrical counterpart, the phenomenon of computation. So on the top you see the representation of the distance function omega xy in terms of the elements of the Moore-Penrose pseudo-inverse. Conversely, we can represent the general term or the element of the Moore-Penrose pseudo-inverse of the Laplacian, which is L plus xy, in terms of the effective resistance distances that are present in the graph between all pairs of nodes. So again, in terms of machine learning or in machine learning language, this is the interplay between the gram matrix or the kernel function and the distance that it computes. They are both interchangeable. Let's take an example. If your graph was a star graph, then you can compute this thing very easily simply by considering the values in terms of effective resistances. Why? Because the pairwise effective resistance between the root of the star and any node is exactly 1 in an unweighted case, whereas the pairwise effective resistance between any other two pair of nodes is exactly 2. They are serial. And using this analogy, we can get a closed form solution for a star graph. But obviously not all networks are as simple as a star or even a complete graph or a chain. Let's look at an arbitrary network case. Let us say that you have a graph GVE shown in diagram A. Imagine that you could break this graph into two parts, G1 and G2, such that both G1 and G2 were connected themselves. So in B, we have created what is called a connected partition or bipartition of the graph, which gives us two subgraphs, G1 and G2 of G, which are independently connected, but you have removed certain edges, which are the cut edges. Now, one could think of the overall graph G as having come about in a hypothetical sequence in the following way. Initially, you had graphs G1 and G2, and then you introduced the first edge ij between them, followed by 3 more subsequent edge additions. So in fact, this tells us that a graph is nothing but a collection of its subgraphs and the edges that you connect between those two disjoint components in a sequential order. We define, so this is the divide and conquer approach that we are going to take in order to compute the pseudo-inverse. The rationale behind this is the following. The overall cost of computing the pseudo-inverse for the full graph is of the order n cube. But if we could divide the graph into 2 parts and compute the pseudo-inverses of those 2 parts separately, that would incur a smaller cost. More importantly, the computation of the pseudo-inverse of G1 and G2 are independent processes. Hence, we can schedule them on independent CPU infrastructures. They have nothing to do with each other. Once you have G1 and G2, now if I could give you a method in which you could use the Laplacian of G1, pseudo-inverse of G1, and the pseudo-inverse of G2, and then combine them using lower than order of n cube computations, then you have an improvement as opposed to computing the pseudo-inverse of the whole. And that is precisely what we are going to do. We first bipartition the network into 2 connected components arbitrarily by removing certain number of edges. And then we reintroduce those edges one at a time back. For each such reintroduction, we have 2 categories. The first category, when the first edge, and it can be an arbitrary choice, is introduced between the 2 connected disjoint components. That process we call the first join. This step is different from all subsequent edge additions because at that point in time you have a singularity where 2 different subspaces have to be combined into 1. For every subsequent, but once you have introduced this first edge, it becomes 1 graph. Hence the spaces, there is just 1 space, they're not mutually orthogonal. And every subsequent edge addition is of the same kind, even though we have to do it separately for each edge. In principle, the methodology doesn't change at all. So let's look at how do we do this.
Yeah, and a quick question.
Well, yes.
Is there any loss, is that when you split a graph into 2 and compute the Laplacian of each and then try to sort of compute the Laplacian of the aggregate using the method you're about to outline, is there any loss of information, or do you pretty much...
Not at all. No, this is an entirely lossless combination. This is not an approximation method at all, and we don't incur any loss of information whatsoever. So that is the beauty of this. So let me show you the first join process. So imagine that at some point in time you had already got the L plus G1, which is the pseudo-inverse of the first graph, for the first graph, and you have the pseudo-inverse for the second graph. Now you introduce the edge ij as the first edge that goes between these 2 disconnected components right now to obtain an intermediate graph G3, which doesn't have the 3 dotted edges that you removed, right? But at this point in time, you now have a connected structure. The general element L plus xy3, meaning in the third graph, G3, can be written entirely in terms of the elements of L plus xy1, which is the L plus xy in the first graph, and in the second graph, and some constants. So there are 3 parts of this formula that you see on your screen. The 3 parts are self-explanatory in some sense. You have to have 3 parts. Why? Because you have 3 kinds of pairs. Of L plus G3, you have 3 kinds of pairs, right? So that is why we get these three cases, which we should have expected. Now, without going too much into the details of how exactly this computation comes about, let me give you a very slight indication of what is the intuition behind this. So remember, we said that there is an effective resistance distance function definable over any graph, right? So take any two nodes that were in G1 before we joined these two guys, right? Because those two nodes X and Y were in G1 already, the effective resistance between those two guys does not change whatsoever because of the introduction of this new edge or this entire new subcomponent. Why? Because if you inserted some current at node X, which was in G1, and you took out all the current in from node 2 or Y, which was also in G1, no current actually goes through this joint edge at all. Hence, the electrical properties of G1 and the electrical interactions between nodes X and Y of G1 stay same after this join. So omega xy G3 for all the nodes X and Y which were in G1 is the same as it were before this first join happened. The same argument symmetrically applies to all those node pairs which were in G2. The only places where we have to make a change are those node pairs in which one is now in G1 and the other one is in G2. But that is a simple linear addition. See, notice why. For any given X that was in G1 and for any given Y that was in G2, what have we done? We are now introducing a bridge edge, which is a single bridge edge between I and J, which connects these guys. But this is a serial resistance addition because now you can rewrite the XY G3 in terms of what was the effective resistance in G1 between X and I, what was the effective resistance in G2 between J and Y, and you simply add to that a term which is the effective resistance of the edge that you introduce between I and J. In the simple case, if the graph is unweighted, this value is always 1, right? Hence, in the first join phase, we are simply relying on the electrical properties of the graph and the fact that resistances added in serial add linearly. Using this simple intuition and some very complex or at least tedious mathematics, we can represent the general element of the L plus xy in G3 as these three linear equations. And I will leave the audience to digest this on their own time, but one thing can be pointed out, that if you look at the right-hand side of all these three equations, you can see that all the terms are only from the L plus G1 and L plus G2, which means that every L plus xy3 term can be computed independently as long as you had L plus G1 and L plus G2, which implies that you have absolute element-wise parallelizability. If you had n square CPUs, you could compute every element of this L plus xy3 intermediate graph simply in terms of in one CPU cycle, which is a major advance. Of course, you have to compute n squared of these guys. But notice, L plus is a symmetric matrix, so you don't have to, in fact, compute the upper diagonal. All you need to compute is the diagonal and the upper diagonal. In fact, the diagonal is also a linear combination of the elements that you compute in the upper diagonal. Hence, you get parallelizability combination at this stage. But we are not done. We still have 3 more edges to add, right? Which are the edge firing stage. So in any case, the next, yes.
Yeah. 2 questions have come in. Would you prefer I hold off so that you can finish?
Let us hold it because I think I'll be finishing it in the next. Cells, you get the white cells for free, which means that if you wanted to compute L plus 1, 1, which is right here, then you just need to add up by doing some simple additive additions of the elements on the left-hand side. You can get that element for free. As I said, L plus is, for an undirected graph, the L plus matrix is a symmetric matrix, hence the lower diagonal comes for free anyways. Now, the second stage was edge firing. And edge firing is a stage in which you introduce an edge between two nodes of a graph which was not earlier present. Remember, we had removed 4 edges from our graph to partition it into G1 and G2. And we have already introduced one of those edges in the first joins phase. So now we have to introduce 3 edges remaining. But all these 3 edges are being introduced in already connected graphs. This is not the same as the edge as the first join case. In which case, we again observe that you can write down this step in which you go from an already connected graph and introduce a new edge into it. The L plus of that new subgraph can be computed entirely in terms of the elements of the previous L plus, as you see in this equation. Once again, I don't want to go too much into detail, but here the L plus xy2 is actually the graph on the right hand side, which is the next subsequent edge-fired graph. And all the elements are computed entirely in terms of the L plus that you had after you computed the L plus for G3, which in this case becomes 1. So it's the first graph. And if, let's say, you wanted to just compute the effective resistances, you can also do that in a similar fashion. So what you're in fact seeing is that, again, you have element-wise parallelizability at this stage. As long as you have all the elements for the previous stage, you will have all the elements for this stage. There is a sequential ordering that is required in terms of edges. All the computations related to a particular edge have to be done at one stage. That's true, but all the computations at that stage can be parallelized entirely. Anyways, so how does what are the scenarios that we can get from here? So think about dynamic time evolving networks. If your network changes, like social networks or biological networks or molecular networks and so on, do you want to recompute everything from scratch just because a new node came in and got hooked to a couple of other nodes? No. Using this methodology, you can do it in order n squared time with some additive cost, and you can recompute the entire matrix in an order of time less cost than if you had to reinvent the wheel entirely. So updates in growth and regress phenomenon, even though I haven't shown the results for regress, all these formulae are translatable to the case in which you delete edges instead of introducing edges and so on and so forth. I think a lot of people who have done structural analysis will be familiar with this preferential attachment model. It's a graph growth model in which rich nodes get richer over a period of time and so on. Again, for that, we can show that the order of time required for computing the updates is only tau squared, which means that whatever number of nodes you had at that time, the squared times that. And again, through parallelizability, we can cut down the costs further. Actually offset the cost. So I wanted to go into the details of how this is implemented, how this insight that when you combine networks in certain ways, you can compute the values simply through increment can be applied, in fact, not just to compute, but to get structural insights into interdependent networks. I will shortly discuss this in 2 minutes just by giving a motivating example. So as I was referring to at the beginning of my talk, in 2003, September of 2003, there was a blackout in Italy. It's a historical case for anybody who studies interdependent networks and robustness, etc., and SCADA systems. What happened was a certain number of communication networks showed a failure due to a power line failure. And that brought down the entire Italian power grid network, which means that the moment you introduce interdependence, the position or the site at which you connect these networks together determines the vulnerability or the robustness of the overall structure. And there is a lot of literature in this regard. The statistical physicists are fascinated and in fact infatuated with what are called statistical properties of the network derived in terms of degrees and so on. These methods can be shown to be very localized and parochial. they're designed in a way to perform certain functions. Remember, so one question you could ask is whether, given two networks that I'm showing here as a chain, if I were to tell you that, okay, join these two networks at one position, just one position, can you tell me which is the best position to join them at? That question can also be answered through the same insights that we saw earlier. Without again going too much into detail, if you had just one thing to join, you would choose those nodes which have greatest topological centrality, which means that have the lowest value of their L plus IIs. And you can show that the same insights that we used in choosing the edge file you go to the periphery first. Counterintuitively, actually, if you have more than one additions that you want to do it at the periphery. In fact, farther away from each other and not at the center. So all our simulations show that to be the case. Once again, we conducted the same experiment on the Italian power grid network, and we showed that if you connected the low centrality nodes or you introduced redundancies between those low centrality nodes in the communication network and the power grid network, you get the most robust structures. But that is only an intuitive thing. If you wanted to prove it mathematically, the formula that I showed in the incremental computation steps actually provide a very good theoretical justification as to why this should be the case. So anyway, so in summary, we have discussed today an incremental computation approach to the pseudo-inverse. We have shown that a divide and conquer based strategy can be used to compute this. You have element-wise parallelizability at each stage, and you can attain an order of time reduction in computational costs if you could do this. Applications are multifarious. Not only does it pertain to multiple fields of human study, but also provides critical insights into the nature of interdependence that you can come across in the networks. So with that, if you have any questions, I'm open to it.
So Gyan, thanks a lot for your talk. Folks, you've just come in under the wire at 1 o'clock. For those of you that need to leave, please feel free to do so. Please do fill out the webinar survey and keep track of the webinar announcements. Our next talk will be on November 21st, I believe. You can see the details up on the website. I guess I'm waiting for questions for people to ask them. Gyan, I think you're going to stay on for a bit beyond 1 o'clock, correct? So let me go ahead. I think there are a few questions that have come in that we have deferred until now. So sure. I guess folks, please ask your questions. But here are a couple that have come in so far. The first one is, if you're adding a resistance element between graphs G1 and G2, then the electrical properties of the whole subgraphs, that is, not just the interconnected nodes, they would change, correct?
No, they won't actually. So no electrical property. If you add only one edge between two disconnected electrical networks, and that is the first one. That's why the first join stage is different from the edge firing stage. If you take two electrical networks and let's call them G1 and call them G2, right? The pairwise effective resistance distance between any pair of nodes which were in G1 will not change if you add one edge to another network. It can be shown through multiple different treatments of the subject. The things that will change, so when the two networks are not connected at all, the effective resistance distance between a node in G1 and a node in G2 is infinity. When you add one unique edge between the two, which is basically a resistive edge or conductance, however you like to call it, at that point in time, the values of pairwise effective resistances between nodes, between node pairs, such that one node is in G1 and the other node is in G2, that changes. But no pairwise effective resistances between any two nodes, either which were both in G1 or which were both in G2, do not change as a result of addition of the first edge. So that part stays.
Thank you. Next question. Of all possible splits of the graph G1 of G into G1 and G2, and I think you might have addressed this in your last slide, what is the best split for high efficiency?
That's a very good question, actually. So first of all, look at the class of problems that, so this is why computational approaches to these things are interesting. First of all, the ideal split would be if you could get n by 2 nodes on one side and n by 2 nodes on the other side with as few edges cutting across them as possible. But the person who asked the question, I'm sure, already knows that that is what we call connected optimal partitioning of a graph, which is NP hard. You cannot do it. In fact, you could relax as many conditions as you like. The problem still continues to be NP hard. But we can play a trade-off cost. Remember that one thing that we want to do is we want to get two connected components, first of all. And then the thing at interplay there, or actually the two factors that interplay are the relative sizes of the graphs G1 and G2. Ideally, they should be half of the overall size, which means that these two should be equal. But you can leave that. An ideal or a good partition would be one in which the edges that go across are not very many. The reason for that is the following. Whatever we did at the stage when we broke G1 and G2 from G can then be recursively done on G1 and G2 as well. So the number of edges that go between the two partitions determines the number of times we have to do all these things. So you have to do one first join and k minus 1 number of edges. That all the relaxed versions of the problems are also NP hard.
Okay, thanks, Gautam. Thanks. Next question. What is the computational complexity of joining the two graphs?
That's a very good question. So the computational complexity of joining the two graphs is only order n squared. So here is the reason. If you believe that you had two graphs and you had the one edge that got fired, recall from the equation, and I will take you guys there on the screen. So it's this equation, right? Imagine that you have one edge going between the two parts. Note that you have to now compute all the n squared elements of the new L plus, right? And as I said, irrespective of the sparsity of your graph, L plus is never sparse. The pseudo-inverse of the Laplacian is a full matrix, period, as long as the graph is connected. Now, so you need at least n squared computations, but for the edge firing, for the first join stage, there are only n squared number of computations. If you even count the scalar computations that you see on the right-hand side, there are roughly 5, because there are some constants that repeat across all the formulae. You just have to compute them once, such as L plus II1, L plus JJ1, L omega ij. These are agnostic to the value of x and y. So n squared is the absolute minimum that you have to do. To be more technical, you have to do kn squared computations, where k is the number of edges that go across your two partitions, because you have to repeat this these n squared computations for each edge that you cut while you created the two partitions.
Thank you. Next question. You pointed out that the L plus computation in general is agnostic to the sparsity of the graph. However, the proposed divide and conquer approach does not seem to be agnostic to sparsity. Do you have a comment?
Yes. So the reason for this is, look, as I said, the computation of L plus using the SVD methods traditionally goes through intermediary computations of all singular values and singular vectors. The moment you do that, and for a good reason, I mean, the people who devised those techniques were not idiots. As I was saying in the answer to the previous question, irrespective of whether your graph was sparse or then the adjacency matrix is sparse. And the Laplacian is also sparse. All you add to the Laplacian is the diagonal values. The problem is that irrespective of the sparsity of the graph, L plus is a full matrix. So you have to compute n squared elements. The reason why our methodology can exploit sparsity of the graph is the following. If the graph was sparse, you would definitely have zones in which you can divide the graph by removing some edges, a few edges. And now you can partition the graph into two sub-problems. All divide and conquer methodologies rely on sparsity of underlying substructures, so what we have been able to show is that, I mean, if there was no parallel between the physical properties of a graph, as in the effective resistance, and the algebraic property, meaning the graph representation, then that would not have been the case. We are simply being able to exploit an underlying property from the field of electricity. Actually, it's not required, but that's a good way to look at it in order to do so. But note, L plus is not a sparse matrix, and therefore there is no way of getting around this bottleneck of n squared. And that stays even in our methodology.
Okay, one more question. Gyan, you mentioned earlier that you could this technique that you talk about applies to weighted graphs too, right?
Yes.
So one question, and of course you've shown a nice model between your graph as well as electrical graphs. One interesting question that might occur, for example, in telecommunication graphs, for example, that occur with negative edge weights. Does your technique handle negative edge weights?
No, communication networks will never have negative edge weights. The concept of cost so let me explain. Maybe you thought of affinities can be both negative and positive, but as long as you don't have mixed values in terms of that is a separate question altogether. Your question is actually a very interesting field of study right now. And those graphs get even more complicated than the ones that we have been dealing with. Negativity of an edge weight would mean that there has to be a physical property in terms of resistance that can take negative values. That is not possible in the physical world. If all your edge weights were negative, that's fine, because that simply means that you, instead of using it as an affinity value, you use it as a distance value, and they are interchangeable. But to answer your question, no, a mixed bag of values cannot be handled by this approach. It cannot be handled by any approach in which you don't treat multi kind of. All you can do is, in that case, Bellman-Ford kind of computations, which give you shortest paths and so on. But no, a short answer would be that we do not address negative weights. But communication networks, I don't think you can express a cost as negative, so might not be a very relevant point.
Okay. Let's see, folks, if you have any further questions, please ask them. Otherwise, I think we're reaching the end of our time here. So we have this tradition, Gyan, that, as you might have seen since you've attended previous webinars, we ask people to, since we're all over the world today, in fact, we have people from China and Taiwan here, so why don't we all give Gyan a warm round of applause for an outstanding talk, and the slides and the recordings will be up online once Gyan and I discuss the copyright issues of uploading such the presentation. So with that, let's go ahead and give Gyan a warm round of applause. Thank you, Gyan, for an outstanding talk. See you all on November 21st at noon Pacific for a talk on by Dr. Quanji Zhu on complex event processing, paradigm for fast data management. And see you all then. And please do fill out the webinar surveys, and I welcome your comments about what we can do to make this better and more insightful for all of you. Thank you very much, and we'll talk to you on November 21st. Bye-bye.
Thank you.